All right, so we're just going to look at the derivative of the inverse sine function. So if we start to have a think about what that might look like, the first thing I'm going to say is just define it as a function. So let y equals sine inverse of x, which implies that x equals sine y, if you just do the same thing to both sides. Because what we're going to do here is we're going to apply some information we learnt about sort of inverse function differentiation, which we looked at in the previous video, which I'll link below. So if you're with me so far, we say x equals sine y, and then we say, all right, dx dy. So the derivative of x with respect to y is just cos of y. So that's nice and easy because we're saying the derivative of the derivative of sine is cos. And so we get dx dy equals cos y. And then dy dx is the reciprocal of dx dy. So we're going to say that that's 1 on cos y. So we've just flipped both sides. And then we can see that cos of y is equal to the square root of 1 minus sine squared y. And you're probably like, why is that true? But I encourage you to think about the Pythagorean identity. Again, I'll put a link below for that if you can't recall. But basically, sine squared y plus cos squared y equals 1. If you rearrange that for cos y, you'll get the square root of 1 minus sine squared y. And the reason we did that is because now we can express the right-hand side in terms of x, because we know from above that x equals sine y, and so the square root of 1 minus sine squared y is the same as square root of 1 minus x squared. And so we can say the derivative is 1 over that, because we saw before that dy dx is 1 over cos y. So therefore dy dx is 1 over the square root of 1 minus x squared. And so we've sort of built up our derivative of the inverse sine function by sort of exploiting the idea of sort of inverse function differentiation and sort of taking the reciprocal. So step that through to make sure you've really wrapped your head around it, and then we can draw the graph. So let's see what that looks like. Just recalling what the sine inverse function looks like. It goes between -1 and +1, and it looks something like that. Now, I encourage you to think about why it looks like that, but remember, it's the inverse of a sine graph, so that you can sort of maybe get a bit of a mental picture in your mind there. And yeah, it goes between -1 and +1, including -1 and +1. We've got asymptotes there, but the reason the asymptotes are there is because the derivative graph, when you sketch it, looks like that, and it has asymptotes at x equals -1 and x equals +1. Now, I encourage you to think about that. The reason that is the case is because if you think about the behavior of a tangent line at near x equals -1, you would see that it become really large and positive. So you can see for the derivative graph that you're getting really large positive values when x is close to -1. And the same thing is happening over at x equals +1. And the intercept of the derivative is actually at 1. I haven't got it labeled there, but the y-intercept of that derivative graph is at 1. And so that means for the pink function, the original function, the gradient around 0 is 1, or the gradient at 0 is 1. So it has a slope equal to, equal to 1, which is the same as the line y equals x. So you can sort of see there that it looks like a nice linear line in the middle there. So hopefully that was helpful. It sort of explains the derivative of sine inverse of x. If you want to challenge yourself, see if you can find the derivative of the cosine inverse of x using very similar logic and see what the graph might look like, and use some online tools or your calculator to visualize that. As always, if you found it helpful, give us a thumbs up. Let us know if you need any private tutoring, and good luck with everything, and I'll talk to you soon.